Good morning, my dear students. Today we are going to discuss about the formation of PN junction diode. So here, most of the semiconducting materials present technological words. That means presently we are using so many types of electronic gadgets like mobile phones, LED display devices, whatnot, many sensors. In so many areas, presently we are using a advanced kind of sensor based application semiconductor devices we are going to use in different areas. For all these materials, the basic semiconductor, the required material is the basic PN junction diode. There is a importance of a PN junction diode. So in this PN junction diode, there we are going to take one P-type semiconductor, extrinsic semiconductor, as well as N-type extrinsic semiconductor. So these two semiconductors are brought together. Like here, I am showing these uh, outline diagram of the PN junction diode. Is it like what I'm presenting on my screen? So here, one part of the semiconducting material is consists of p-type. P-type means positive type charge carriers. Other side, you may have n-type negative charge carriers, majority charge carriers on other side. So these such two dissimilar type of majority charge carriers are brought together, which will give a formation of junction diode. The junction is the surface boundary race where we are going to contact the two dissimilar extrinsic semiconducting materials together. So that boundary we can call it as a junction. As I'm showing here, this junction diode material here I'm showing now. So this is the junction layer. This is the cross section. There is a main interconnecting, like acts as a bridge between the two different extrinsic semiconductors. Okay, so here, as I discussing that, here on the P side, we have the majority charge carriers are holes. Nothing but they may are called as technically acceptors. On N side, you may have excess number of electrons. In the technical term, we can call it as a donor ions. Okay. Now, these two materials are brought in contact at the boundary surface areas. On the boundary surface area, this is the boundary surface. On the both sides, you may have 1 plus 1 neg, 1 plus 1 minus. These opposite kind of charges are gets attracted, gets neutralized. So here this positive negative ions gets neutralized. So in this particular region, the charge carriers gets neutralized. Due to the neutralization, you won't have any type of charges in the particular region. So that region we can call it as depletion layer or barrier, potential barrier. Okay, so this is the region where you don't have any types of charges. Why? Because all the charges are get recombined recombined due to the attraction, due to the opposite kind of charges. That particular charge areas where the influences each other, where the charges can influences each other, comes closer, one positive one negative coming closer, then these of attractional force, these opposite kind charges gets neutralized. So there, that region we can call it as a depletion layer or potential barrier. This barrier will oppose the charges, the remaining charges. What are the remaining charges on P side and N side? Those charges is unable to cross the particular barrier. Why? Because that acts as a one what we can call it as a barrier. Barrier means which is obstacle to flow the charges from one side to another side. So suppose in the semiconducting point of view case, if you want to have the conductive mechanism, what we need to do here, we need to flow the current from, or we need to apply the potential difference between the two terminals. There you may have the flow of current in the particular PN junction diode that can be achieved with the help of biasing cases. What is the meaning of biasing cases? One is forward biasing case, another one is reverse biasing case. That means what happens, what is forward bias and what is reverse bias, what happens in these two cases also we need to discuss. So here in the forward biasing case, what we are going to do here, this forward bias case, the P terminal of an extrinsic semiconductor is connected to positive terminal of a battery. Positive terminal of a battery. So here I'm going to take this P-type terminal. Extrinsic semiconductor is connected to positive side of a battery. Like here also, the N-type semiconductor, extrinsic semiconductor is connected to negative terminal of the battery. So here on the sides you can observe these two are same kind of connections. Same kind of connection means majority charge carriers are positive, which is connected to positive terminal. That means as per the basic knowledge, the same like charges gets repelled as per the basic laws. The same kind of charges gets repelled at positive. That means the positive charges repelled by the positive terminal. So that what happens, the majority charge carriers of holes on P side will be repelled. So due to this repulsion process, these positive charge carriers are trying to cross this barrier. Basically, the depletion layer or barrier having certain voltage to oppose the flow of charges from P side to N side, similarly from N side to P side. Now, what happens here? Gradually, you are increasing the barrier, applying voltage. Applying voltage. You can increase the applying voltage on this PN junction diode. If you increase the voltage, due to this applying voltages, the repulsion gets more and more. So due to this repulsion, these same kind of charges means holes are trying to cross the barrier. That means what, up to one particular point, the barrier can sustain the opposition forces. After reaching the saturation voltage that is equal to the barrier potential, after crossing the particular barrier potential, what happens? These charges, majority charge carriers of holes on P side is trying to enter into the N side. Like the same pattern, N side electron are trying to enter into the P side. That means which lead you the flow of charges nothing but current. That means gradually after crossing the particular voltage, the charges are trying to enter into the other kinds. So that will lead you the flow of charge nothing but current. So the current value gradually increases. So that current value increase variation that you are going to observe in the previous diagram. Here it is, the diagram. Here is the diagram. So in the diagram, you will observe this is the forward biasing case where you are taking voltage on x-axis, current on y-axis. Here you are getting maximum currents. That's what the current value observed in milliamperes case. Okay, so up to certain voltage, there is no that much of variation in the current value. After reaching the particular voltage, suddenly the current value gradually increases and becomes maximum. So at what particular point the current value starts to increase, that particular point we can call it as a knee voltage. The particular voltage we can call it as a knee voltage. That is the case of forward biasing case. Similarly, you can do the same process in the reverse bias case. In the reverse bias case, what we are doing here, the P-type extrinsic semiconductor is connected to negative terminal of the battery. That means here opposite kind of charges. Like here also n-type extrinsic semiconductor is connected to positive terminal of the battery. So opposite charge kind of charges will get attracted. So that what happens, these holes get attracted towards electrons. So majority charge carriers are gets neutralized. So what are the remaining charges here? Minority charge carriers are electrons. Now here in this case, the depletion layer width value increases. So here what happens, if your depletion layer value increases, means barrier strength increases. That means you need to apply more and more negative voltages to the particular case to get a minimum value of current. That's what here we are observing the reverse bias case in the third quadrant, that is in the negative direction cases. Okay, here also the variations gradually very small up to certain voltage. After reaching certain voltage, suddenly the current value increases. So that current is nothing but we can call it as a reverse breakdown voltage. Reverse breakdown voltage. Reverse breakdown voltage. So this is the forward and reverse biasing condition, which will help you how the conductivity behavior is going to be observed in the particular semiconductor diode materials. And this is the basic diode, and this diode can able to convert into different types of semiconductor devices like LEDs, solar cells, photodiodes. This is the basic component of a semiconductor device, and this semiconductor device will be represented in a symbolic manner like this. This is the symbolic representation of a diode. I think everyone knows about the symbolic representation. Here on this side it is a anode, it is a on this other side it is a cathode K. So this is the symbolic representation of a PN junction diode and its reverse biasing condition, and that we are going to be explained with the help of this, the characteristics, IV characteristics of a PN junction diode also. Okay, that's it for today. Thank you.